Program testing can be used to show the presence of bugs, but never to show their absence. This is a famous quote by Edgar W. Dijkstra. In this video, I will not only show you how to write unit and integration tests for your Rust program, but also how you can structure your code for better testing and scalability. Unit and integration tests are two different approaches for examining your code. Unit tests zoom in on individual functions or components, testing them in isolation from the rest of the program, like checking if a gear pair works correctly. Integration test, on the other hand, pulls back to see how these pieces work together, similar to testing how all the gears fit together to produce the desired result in a complete machine. Most times, a function will depend on other functions and structs. If you write a unit test for a function that uses all of its dependencies, the test will fail if one of its dependencies fail. For example, a function that calculates the total price to pay will depend on a function that calculates the total price of the goods, a function that calculates the tax to pay based on the price of the goods, and then a function that evaluates the discount based on the coupon code provided. If I write a unit test for this function as it is, and one of these three functions returns a wrong value, the unit test for this function will fail. When writing a unit test for this function, you would want to isolate this function from its dependencies, but when we write an integration test for this, you would want to include all of its dependencies. I will show you how you can do this seamlessly in this video. While tests are typically written during development, in this video we'll write both unit and integration tests for an almost completed program. You will learn so much from this video even if you're already familiar with writing tests in Rust. I will show you how to examine the test coverage of your program and how to get a detailed report in an HTML file, which you can then open through the browser. I'll walk you through all the assert macros available in Rust, all the test attributes, how to filter your tests, and other best practices you should observe while testing your program. The program which you write unit and integration tests for is this calculator program. When running the program, I insert the expression to be evaluated as an argument, and the program then prints the result to the terminal. This handles operations such as addition, subtraction, multiplication, divisions, and also exponents. You can also add parentheses to your expression to change the order of evaluation. To follow through with this video, you can clone this repository on GitHub and write the test alongside this video. There are two branches, the main branch without the test and another branch that contains the tests. I will drop the link in the description and pinned comment below. Let's start by writing basic unit tests. When I create a new Rust project, which is a library crate, and open up the lib.rs file, you can see a function and a unit test for that function. Another difference between writing unit and integration tests is that unit tests are commonly written in the same file as the function. But for integration tests, we will need to create a directory called tests at the root of the project, and that is where all the integration tests will belong. Below this add function, we have a module named tests, and right above this module, you can see a CFG attribute added to the module with test as its argument. This attribute lets the compiler know that this module should only be compiled when we are running a test. Within the test module, all items from the parent module are imported into the test module using the super keyword. This also includes private resources. To show you this, I will create a private function which I will name subtract. I can use this function within the test module. This is because a child module can use any resource from its parent regardless of its visibility. With this, you can deduce that unit tests can use both private or public resource from the parent module, unlike integration tests which you'll come across later on. The test attribute here marks this function as a test function. Any function included in this module but without the test attribute won't run. To check this out, I will include a function without the attribute and then test the program by running cargo test in the command line. You can see from the logs that only one test named it works ran. The assert EQ macro here is used to check if two expressions are equal. If the value on the left is different from the one on the right, the test fails. You can also have multiple assertions in one test function, and they all need to pass for the function to pass. There are other assertion macros in Rust. There is an assert macro which checks if an expression is true. If the expression is false, the test will fail. You can use an assert macro in place of an assert EQ macro by comparing the left and the right with an equality operator. As we have the assert EQ macro that checks whether the left and the right values are equal, there is also the assert NE macro, which verifies that the left and the right values are not equal. If their values are equal, the test fails. If I run the test with result and 4 as the values in the assert NE macro, our test fails since the value of result is 4. You can also pair an assert macro with a matches macro to compare a value against a pattern, similar to the match operator. For example, let's say we have an option enum with a sum variant containing the integer 5. We can assert that this variable is a sum variant by combining the assert and the matches macro. On the left side of the matches macro, we insert the variable, and on the right, we give the pattern to be matched with. So if you wish to verify that the option variable is sum, I will insert the sum variant and set its value as underscore for now. When I run the test, it passes. If I set this to none and test again, it fails since the variable does not match the pattern provided. The matches macro compares the value with the pattern and returns a boolean indicating if they matched. For a more complex case, let's say the variable is a sum containing a tuple with values 5 and 7. I want to assert that the value at the left of the tuple should always be less than that on the right. So in the pattern, I insert the variables x and y and add that x should always be less than y. If I run the test, it passes. But if I replace 5 with 8 and run again, it fails. There is an assert matches macro that gives a more detailed failure message, but it is only available in nightly Rust as of the time this video was made. There is a lot to unit tests and we will go through them when we write tests for the calculator program. So here is a diagram of the code base. The calculator has 6 evaluators. Each evaluator is an integration of some components. We will write unit tests for each component, an integration test for each evaluator, and an integration test for the calculator, which is an integration of the evaluators. Once you have cloned the repository, open the cargo.toml file. There you will notice that we make use of 2 crates. This error for error handling and regex for writing regular expressions. Before we start writing tests, let me give you a tour of the code base. In the main.rs file, the expression is extracted from the argument passed when we run the program. The args function here returns an iterator over the arguments. The first element is the path to the program's binary, so we skip it. What we need is the second element of the iterator, and that is the argument we pass right after running the program. If I add a space and another argument, this will belong to the third element and so on. I used a quote in the first argument to prevent these spaces from being treated as another argument. This not only works with cargo run, but you can compile the program into a binary and pass the arguments the same way. Let's go back to the main.rs file. After skipping the first element, which is the path to the binary, the next method is called, which returns an option enum containing the expression. If there is no expression, this message is just printed to the terminal. But if there is, we call the calculate method from the calculator struct, which is imported from the library crate. This will return either a 64-bit float or an evaluation error if it encounters one. If you go to the lib.rs file, you can see that the calculate struct implements the calculator trait, and the evaluators function returns a vector of functions. The expression string will be passed through all these functions, which will evaluate it. So let's take a look at the calculator trait and see what it does. You can recall that in the main.rs file, the expression is passed into the calculate method. In the calculate method of the calculator trait, the string is passed into the evaluator functions. Each evaluator function takes in a string and returns a result enum, whose success value is a string, and the error is the evaluation error. So the evaluators method is called, and the vector returned is converted to an iterator. Since each evaluator function returns a result enum, we use the trifold method instead of a fold method to reduce the iterator into a single value. The trifold method takes in an initial value, which is the input in this case, and its second parameter is a closure. The first parameter of the closure is the accumulated value from the previous iteration, while the second parameter of the closure is the current element of the iteration. The function is called and the accumulated string is passed as its argument. If one of the functions returns the error variant, the trifold method returns the error, but if it succeeds, the string is passed as the accumulator in the next iteration. The result, which is a string, needs to be converted to a float, so we make use of the parser function. The parser function in this trait just wraps the parseValue function. So why didn't I just use the parseValue function here? Well, if I used the parseValue function here, then this calculate method will be coupled with the parseValue function. So when I perform a test for the calculate method, if the parseValue function returns a wrong value, the test for this will fail, and where the bug comes from will be hard to locate, since the bug may come from one of these evaluators or the iteration. If the parseValue or evaluation function doesn't work correctly, the bug should be detected at its own unit test. When I write a unit test for the calculate method, I just want to make sure that this iteration I did here works as expected. Therefore, I will mock up some simple evaluator functions and a simple parser function. To see this, let me write a test for the calculate method. So just as I showed you at the start of this section, create a module named tests. You can name it whatever you like, but tests is the naming convention for the test module in Rust. Next, I will use the CFG attribute and pass in test as its argument. We can then import all items from the parent module into this test module using this statement. I will create a test function which I will name testCalculate method. And remember to add the test attribute to this function so the test runner can know it's a function to run during tests. Next, we will create a mock calculator and implement the calculator trait for this struct. For the evaluators function, I will return a vector of mock functions, which I will create below. I named these functions mock function A, mock function B, and mock function C, and all they do is add the string slices A, B, and C to the string and return the results. For the parser method, since we have already defined a procedure for this method, it is not required as it will use the one we provided in the trait definition by default. Here we want to test just the calculate method. So we will mock the parser method as well. For the mock definition, I will test if the input ends with ABC. That is, if the evaluator functions were used correctly and yielded the correct results. If it did, I will return the OK variant with 1.0 as its value. If not, I will return the evaluation error. In the test function, I will assert that the return value of the calculate method is an OK variant containing 1.0. When I run the test, you can see that the test for the calculate method passed. You can see that other items are printed on the terminal. The first section contains tests for the library crate. The second contains those for the binary crate, which will be written in the main.rs file. The third contains the doc tests, which we will discuss in another video. Another set that is not included here is the integration tests, which we'll come across in the next section. To run tests only for the library crate, add a leap flag and only tests for the library crate are run. For the doc tests, add a doc flag. To run the test only for the binary crate, add a bin flag, but you will need to add the name of the binary, since you can produce more than one binary from a Rust program. We only have one binary named calculator, so I will follow this with calculator, and when I run, only the test for this binary will be run, which is 0 for now. To run the unit tests in all binaries, use the bins flag. For running only integration tests, we will use the test flag followed by the name of the file. I won't show you how to use this now, but we'll come across that later on. So the test for the calculate method passed, meaning that the iteration worked as expected. If I change this B to D and run the test again, the test fails. I ran this test with the leap flag to filter the other output. If I have other tests on the library crate, it will show up here as well. To run only the calculate method test, you can filter the test by name. Before I do this, I will fix the test, and after the leap flag, I will add the name of the test. Now when I run this, only the calculate method test ran and it passed. A test function can also return a result enum for convenience, but its success value should be a unit. I can change this function to return a result enum. I will set the success value as a unit and the error value as an evaluation error. Now, since the calculate method returns a result, I can propagate the error using a question mark and replace this with just 1.0, but you should return an OK variant containing a unit at the end of the function. With this, we are able to test the procedures of the calculate function isolated from its dependencies. Sometimes a function may only depend on one or two other functions. Setting up a thread for this might be an overkill. In this case, you can use dependency injection. For example, the calculate function could be written as this. Here we take in the evaluators and the parser function as a parameter. When we write a unit test for this calculate function, you can then pass in a single mock parser function and some simple mock evaluator functions. When integrating this calculate function in the main program, you can then pass in the actual parser function and evaluator functions. The limitation of using this method is when your function makes use of several dependency functions, which may still make use of other dependency functions. When you state these dependency functions and their types, or try to integrate a function with so many nested dependencies, your code can get a bit ugly and difficult to manage. So you can always gauge and pick the best approach when rewriting your functions for tests. I said rewriting here because the first time you write a function, your top priority is to get the function to work as expected. After that, you can then restructure it to make it cleaner, easier to test and scale. Now let's take a look at the parse value function. This takes in a string and returns a result enum containing a float or an evaluation error. The string from the parameter is converted into a float using the parse method. This returns a result enum containing the float or a parse float error. I then converted the parse float error to an evaluation error using the map_err method. One good benefit of writing extensive and rigorous unit tests for a function is that someone can figure out what a function does by inspecting its input and output in the test cases. For example, here are my unit tests for the parseValue function. Looking at these, you can see that it takes in not only integer and decimal values, but also scientific notations. We can also parse values such as inf, infinity, their negatives and none as well. You can also see that any other value will result in an error, including spaces in the string. Let's run the tests again. You can see they all passed, and the tests in the parser.rs file along with other tests were run. To only run the test in the parser.rs file, after cargo test you can add the lib flag, and since the parser.rs file belongs to the utils module, I will enter utils followed by 2 colons and then the parser module. Now only test from the parser module run. To run only test from the calculate module, replace this with the calculate module. Before we write more tests, let me show you how you can calculate the test coverage in your program and get a nice and detailed HTML report showcasing your code coverage. First, you would have to install a binary from Cargo called cargo-tarpaulin. So in your terminal, run the command cargo install cargo-tarpaulin. When this is done installing, you can run the command cargo-tarpaulin. This will compile the program, run the test and output your test coverage. Right now we have a very low test coverage of 7.23%. To get a more detailed result, we can get a HTML output of your test coverage by adding an out flag with HTML as the value. Now at the root of your project, you can see a tarpaulin report.html file. When I open this file in Chrome, you can see that the calculate.rs file has a 60% test coverage as we only wrote a test for the calculate method and not the parser method. This parser method will be used in integration tests, so we won't have to worry about that for now. If you head to the utils/parser.rs file, you can see it has a test coverage of 100%. Since the parseValue function, the only function here, is tested. I'm going to write more unit tests to bring up the test coverage. After that, I will introduce you to some test attributes. You can use these attributes to control how your test should behave. I have written some unit tests for the formatters module, the extractor, the evaluator and the regex module, which you can access by switching to the with test branch in your cloned project. But let's take a look at the evaluator module. Here I want to test the evaluate method of the evaluator trait. Like the calculator trait, we have other functions that are dependencies for the evaluate function. The evaluator trait takes in a generic n, which denotes the number of operands the evaluator takes on. For example, a parenthesis evaluator takes one operand, which is a string contained in the parenthesis, while an addition evaluator will take two operands, which are the two numbers beside the plus sign. In the evaluate function, the operands are extracted from the string and then converted to a float. The operation is performed on the operands and part of the string operated on is then replaced with the result. This process is then repeated until no operand for that evaluation is found in the string. You will understand this better when we look at the test for this function, which is one of the big benefits of writing tests. So in the test module, we have a mock addition evaluator struct, and I implemented the evaluator trait with n as 2 for the struct. This implies that the extractor will return an array of two string slices, which are the operands, and the operator will accept an array of two floats as a parameter. The regex function is only used in the default extractor function. Since we are mocking our own extractor function and this won't be making use of the regex function, I added an unreachable macro here, asserting that this function will never be called. If this function gets called, our test will fail. I created a simple mock for the parser and formatter function, and for the operator function I returned the sum of the two operands in the array. In the extractor function, if we have the string 2 plus 2 plus 3, it should return 0 as the start of the match and 5 as the end of the match. This means that the substring to be replaced is 2 plus 2. The operands 2 and 2 are then returned in an array. This will then be converted to a float by the parser function. The array of floats will then be sent to the operator function. 4, which is the result of the operation, will then replace the substring 2 plus 2. Now when we have the string 4 plus 3, our operands will then be 4 and 3. In the test, when I evaluate the string 2 plus 2 plus 3, it should have 7 as the result. When I run the tests in the evaluator module, you can see that the test passed. Before we move to integration tests, let's look at some test attributes. These are attributes you can add to your test function to change its behavior. To do that, let's head to the extract regex captures function and look at its unit tests. What this function does is that it accepts a string and a regex and then returns an array of the captured substrings from the string using the regex. It also returns the start and end position of the entire match. Since it returns an array, the size should be fixed, but at the same time, the size could vary, since we have no idea of the number of captured groups contained in the regex. So what we do is to add a generic n indicating the number of captured groups in the regex, which will then be used as the size of the array. In case you may not be familiar with what a captured group is, here is an example. Looking at this regex, after I remove the parentheses, this matches a string that starts with a word followed by a colon and some digits. This will match the whole string here since it begins with a word followed by a colon and then some digits. Sometimes you may want to extract some substrings from the match. In this case, I want to extract the word and the digits excluding the colon. What I will do here is to add a capture group around the word and digits. So in the regex, I will add a parenthesis around the word and then the digits. Now when I call this function, I will pass in 2 as the number of capture groups. I can now assert that the captures from the string are test and 1, 2, 3. If I add a prefix, a suffix, and even another match, this function only captures the first occurrence of the match with its start and end positions. The extract regex captures function returns this tuple in an option enum, meaning that if there is no match, none is returned. Now let's look at a case where we have just 2 capture groups in the regex, but then specify 3 in the function. Well, the function will panic. To assert that it does, I added a should panic attribute to the test function. If I remove this and run the test in the module, you can see that the test fails, stating that the function panicked and we asked for 3 groups, whereas we should have asked for 2. If I put back the attribute and run the test again, it passes. If I replace 3 with 2 in the function and run again, the test fails since the function didn't panic as we expected. When a function panics, sometimes it panics with a message. In one of the previous tests, the message was asked for 3 groups but must ask for 2. To be sure it panics with the correct message, you can add an expected argument to the should panic attribute with the message. If we run this test with 3 as the number of captures, it passes. But if I change this to 4 and run again, the test fails because the panic message did not match. In this case, the panic message is asked for 4 groups but must ask for 2. Another attribute is the ignore attribute, which is used to stop a test from running. This is used in special scenarios like if the test takes time to run, or an integration test needs access to a database or performs an API call and the authorization is yet to be set up. In this case, I use the ignore attribute in this test function. If you want a message to be displayed to the terminal when this is ignored, you can add the message in the attribute after an equal sign. To run all ignored tests, add the ignored flag after 2 hyphens. There is also a bench attribute you can use to benchmark your programs, but I will cover that in another video. Now that I have added some unit tests to the program, let's test the test coverage of our program. So in the terminal, I'll run the command cargo-tarpaulin with HTML as the value of the out flag. You can see that the test coverage is now at 45.78%. When I check the HTML report and open the evaluator.rs file, you can see the other functions in this thread are highlighted with red. This will all be covered in the integration test along with the items in the lib.rs file. Just like in test, you can skip some file when calculating test coverage. To skip the main.rs file and calculate the test coverage for the library crate, add the library flag. When we run the test again, the test coverage goes up, and when you check the HTML report, the main.rs file was excluded from the test coverage. You can also exclude individual files using the exclude files flag followed by the 5 parts of the file to be excluded. I will exclude the source/lib.rs file and the source/calculate.rs file. After the test coverage is calculated, you can see that the test coverage percentage went up by a significant amount. Now let's write some integration tests for the program. When writing unit tests, the tests were written in the same file as the function. For integration tests, we will have to create a directory with the name test at the root of the project. This directory will contain Rust files, and in those Rust files, you will write your integration tests. Each Rust file in this directory will be compiled as an individual crate. For example, I will create a file that I will name calculate test to test the calculate method of the calculator trait. Integration tests are dedicated test files, so you do not need to add a test module or CFG attribute here. You can start by creating a test function using the test attribute. I will create a test function called calculate addition and then import the calculate struct and the calculator trait from the library crate. In this function, what I will simply do is assert that passing the string 1 + 2 + 3 will return an OK variant containing the float 10. When I run cargo test this time, you can see a new section running the test from the file test/calculate.rs. To run tests that are only contained in this file, add a test flag followed by the file name, which in this case is calculate tests. To run only the integration test to your program, after the test flag, add an asterisk contained in a single quote. Since we have only one integration test file, we just have that file in this list. Let's calculate the test coverage this time, and when this is done, you can see an increase in the test coverage. Let's check out the HTML report. When I open the source directory, you can see that the calculate.rs and evaluate.rs file now has a test coverage of 100%. This is because every function or method in this file was used in an integration test. Let's check out the lib.rs file. When I open this, you can see that the operator function for every evaluator was not covered in this test, apart from the addition evaluator. This is because in the integration tests, the string only contained addition operations. You can write more rigorous tests and bring up your test coverage. You can also write dedicated tests for each evaluator. For example, you can create an integration test for the division evaluator. I will name mine division tests. In this file, I will import the division struct and the evaluator trait. I will then create a test function for a simple division case. Before I end this video, a common situation you may come across is how you can reuse a function between your integration tests. For example, let's say you have a function called setup where you initialize the config and some other resources for running your integration tests. Instead of rewriting this function in every test file, in your tests directory, create a file called common/mode.rs. Here, you can define a setup function and make it public. In your integration tests, you can then include the common module and import the setup function. That is all for this video. Thanks for watching.